Next thing we're going to talk about is properties of alcohols and ethers. We're just going to talk about properties of alcohols. Okay, so an alcohol, it's sp3 hybridized. Your bond angles technically should be approximately 108.5. All right, I'm sorry, 109.5. But because of the lone pairs, it actually squeezes this bond in just slightly a little bit, and it's somewhere between 108 to 109. I mean, it's not that far off, but your lone pairs technically are much larger groups. Remember, your lone pairs are spheres of electrons, so they actually have a little bit of crowding going on. So they actually squeeze your carbon groups a little bit closer together. The other thing that alcohols have is hydrogen bonding. All right, hydrogen bonding, we've talked about, is a really important property in molecules. And remember, it's between a lone pair and a polarized hydrogen. All right, so what does this do? This drastically affects the boiling points. So if you take methane, and if you take methyl chloride, and if you take methanol, very similar compounds. The difference I'm changing is a hydrogen in the methane, a chlorine, which is a very large group, and then the hydrogen bonding. You can see that the boiling points drastically change. Okay, in the methane you have van der Waals forces. Boiling point is -50. Remember, those are the van der Waals forces, or the London dispersion forces. With the methyl chloride, you have dipole-dipole bonding. So the boiling point is still much higher than methane, but still pretty low, -5. This is degrees Celsius. And then your methanol, 50. Okay, so there's a difference of 100 degrees Celsius. By putting on an OH group with hydrogen bonding. That's a huge effect. Just to kind of show you how important hydrogen bonding is. The second property I want to talk about is acidity. Okay, and this is really the more important part I want to talk about. All right, oxygen is relatively electronegative, so it can stabilize a negative charge. Stabilize negative charge. So because of that, alcohols are relatively acidic, and the more that the electrons could be stabilized, the more acidic that alcohol. Okay, I think I actually spelled stabilize wrong. That should be an I there. All right, so let's look at some acidities of alcohols. Now, just remind you, acidity is based on pKa. Okay, a pKa of about 50 are things which are not acidic at all, like hydrocarbons. All right, hydrocarbons are not acidic. It's like our gasoline and oils. And a pKa of about a pKa of 4, not -4, but about 4 is vinegar or acetic acid. Okay, just to kind of give you the two extremes. Alcohols, depending on the type of alcohol, just a garden variety ethanol. All right, ethanol is drinking alcohol. Has a pKa of about 16. Okay, just to kind of give you something about the acidity, it's about as acidic as water. Water is roughly around there. Phenol, so here's what's going to become interesting. Phenol, all right, you have an OH attached to an aromatic ring. That has a pKa of about 10. All right, so it's about 10 to the 4th times more acidic. So it's 10,000 times more acidic than just ethanol. And it's because of resonance. All right, if you were to take phenol and deprotonate it, so add in some sort of base, all right, and the base will pluck off the hydrogen and the lone pairs go on the oxygen to give it a negative charge. All right, this is a stabilized ion. Why is it stabilized? Because the lone pairs can actually form resonance structures inside your ring. I'm not going to show all the resonance structures, but you technically have 3 more resonance structures. So due to resonance, you can stabilize, I just can't spell stabilize today. You can stabilize that negative charge. With ethanol, if you add in a base and deprotonate it, you just have a negative charge on the oxygen. This is not stabilized. All right, I spelled it right that time. All right, so that's not stabilized. But with the aromatic ring, you have a stabilized molecule, so the acidity is much lower. If you put on electron withdrawing groups, or groups that have more, that add more resonance structures to your molecule, like a nitro group. All right, here's a nitro group. If you add in a base, you deprotonate it, and you form the negative charge. All right. Notice you have another pi bond adjacent to your aromatic ring. So the lone pair can drop down. These can go into here, into here, and you even have another pi bond to actually form a fourth resonance structure. Nitrophenol has a pK of roughly 7. Okay, so we're drastically making it much more acidic. There's actually something called trinitrophenol. This is extremely acidic. The pKa, I believe, is close to the negatives, which is what strong acids are, like hydrochloric acid. Okay, because now you have 3 nitro groups, so you have 6 more resonance structures. So let's just say this is very acidic. In fact, I just looked up the pKa of trinitrophenol. The pKa is 0.40. I mean, it's almost 0. So it's extremely acidic. This is actually called picric acid. Right, and this compound is actually very explosive. I believe it's stored in water. It's stabilized in water because of the hydrogen bonding, but if it dries out, it becomes very shock sensitive. If you notice, it's kind of like trinitrotoluene, remember, which is TNT. You would have a methyl group in place of the OH group. That's trinitrotoluene. But this compound is a little bit more shock sensitive, a little bit more explosive than trinitrotoluene. Another property of alcohols is its ability to form alkoxides. Okay, and alkoxide, we've been learning a lot about these with SN1 and SN2, mostly SN2 reactions. And alkoxide is a compound that has an O negative. Okay, you know that we've just been using those when doing reactions, but how do you actually make alkoxides? All right, well, they start with an alcohol, and you just add either sodium metal or potassium metal or lithium metal. Okay, you actually just add the metal, okay, the element. These metals are not found in nature. They're extremely reactive with acidic protons. I don't know if you've ever seen anyone take a piece of sodium and throw it into water, but it starts to fizz and bubble, and you form hydrogen as a byproduct, which is explosive and it's flammable. So you actually see an orange flame actually form on the surface of water, because as the hydrogen is evolving, the reaction is exothermic, and it creates enough heat to actually ignite the hydrogen. But basically what happens is, in this case, if you take sodium metal, add it to an alcohol, you form the alkoxide with the sodium counterion plus H2 gas, but that all bubbles away. So this is the first reaction of the chapter, a way to make the alkoxide. If you use the potassium, you form the potassium ion. The potassium ones are usually more reactive, and then you can also form the lithium one if you want the lithium. That one's kind of least reactive. The sodium one is it's like the Goldilocks analogy. It's the perfect one. Alkoxide.